Tonight, we will talk about a question that feels almost too strange to be true. Is the past still out there? Whether you're listening to fall asleep or to explore the hidden layers of time, space, and reality, you're in the right place. So relax, settle in, and let's begin a quiet journey through one of the most curious mysteries science has ever faced. Let's start with what we think of as the past. You might imagine your childhood, the smell of an old classroom, or a memory from last week. These recollections feel like echoes, like they happened and are now gone. But is that truly what the universe does with time? Does the past vanish, or does it persist in some hidden way, folded into the fabric of reality? At first glance, it seems obvious. The past is over. You can't touch it, revisit it, or change it. But science, especially modern physics, paints a more unusual picture, one where time might not be a flowing river, but instead a vast landscape, where every moment still exists somewhere, waiting. Our ordinary experience of time has a direction. It flows from past to present to future. This is called the arrow of time. We age, we remember what came before, and we cannot change what's already occurred. This seems so natural that we almost never question it. But scientists do. And what they've discovered is that this arrow of time is deeply tied to something else: entropy. Entropy is the measure of disorder in a system. According to the second law of thermodynamics, entropy in a closed system will always increase over time. A glass of hot tea left on a table will cool down. A house left untouched will slowly fall into decay. This increase in entropy gives time its direction, from order to disorder. But if you look at the fundamental laws of physics, those that govern atoms, particles, gravity, even light, you'll notice something strange. These laws don't prefer any direction. Whether time moves forward or backward, they work the same. In other words, the microscopic rules of the universe don't actually care about past or future. That's our first clue that the passage of time might not be a fundamental feature of nature. Instead, it could be something that emerges from complexity, something that arises from the way we, as conscious observers, interact with the world. If that's the case, then perhaps the past hasn't disappeared at all. Maybe it still exists, we've just lost access to it. One theory that tries to explain this is called the block universe. Imagine the universe not as something unfolding moment by moment, but as a single, four-dimensional structure. In this model, space and time are like a frozen loaf of bread. Every slice represents a moment in time, from the birth of the universe to the far future, and all slices exist simultaneously. They're not flowing, they're just there. You're in one of those slices right now, experiencing what feels like the present. But in this view, the past is not gone. It's just a different slice of the same cosmic loaf. Your first birthday? Still there. The extinction of the dinosaurs? Still there. Even the moment the first atoms formed? Also still there. This idea isn't science fiction. It's a natural extension of Einstein's theory of relativity. In special relativity, time is relative. It moves differently depending on how fast you're moving. If two people are traveling at different speeds, they'll experience different rates of time. In some situations, what one person sees as now might be in the past or future for someone else. This destroys the idea of a single, universal present. Instead, every observer has their own present moment. And from that comes the concept of spacetime, a four-dimensional arena where all events, past, present, and future, are laid out together. Nothing flows in space-time. Everything just is. Let that sink in. If the block universe is real, then the past hasn't been destroyed. It's part of the structure of reality, just not accessible to you in this moment. But if that's the case, why can't we go back to it? That brings us to the nature of causality and information. The universe operates under rules that seem to prevent backward movement through time. One reason is that causality, cause and effect, must be preserved. If you could go back in time and change something, you'd create paradoxes. These paradoxes could break the consistency of the universe. For instance, the famous grandfather paradox, where you go back and prevent your grandparents from meeting, thus erasing your own existence. Physics doesn't like paradoxes, so one solution is that the past may exist, but it's unreachable. Like a painting on the wall of the universe, eternal, preserved, but behind glass. Still, there's a loophole. Light. Light takes time to travel. When you look at the moon, you're seeing it as it was 1.3 seconds ago. When you look at the sun, you see it as it was 8 minutes ago. The farther away an object is, the further back in time you're seeing it. That's not poetic, it's literal. Some galaxies are so far away that their light has taken billions of years to reach us. The light we see tonight from them began its journey when Earth was still forming. In that sense, telescopes are time machines. They allow us to see the universe as it was long ago. So let's ask the question again. Is the past still out there? If we take a step back and think in terms of light, then yes. The past is physically encoded in the photons moving through space. It's floating around us, always. With the right technology, in theory, we could read that light like a book. In fact, scientists are already doing something like this. In astronomy, researchers use light echoes to reconstruct the history of cosmic events. When a supernova explodes, the light illuminates nearby dust, and that light bounces off in different directions. By capturing those echoes, astronomers can effectively rewind the explosion and study it long after it's over. It's like watching fireworks reflected in distant windows long after the original show ended. This concept could be extended to everything. Every event on Earth, every step you've taken, every conversation ever had, sent light scattering into space. That light is still travelling. It's unimaginably faint and scattered, but it's out there. Now imagine an unimaginably advanced civilization far away in space, with the power to collect and reconstruct these ancient photons. They could, theoretically, watch Earth's past unfold like a movie. They wouldn't need a time machine. They'd just need a powerful enough eye. Does that mean the past still exists? If it can be observed, even in principle, then in some ways it must. There's another wrinkle to consider. Quantum mechanics, the science of the very small, has its own perspective on time. In some interpretations, particles don't have definite histories until they're observed. In others, time is fundamentally symmetrical. Still others suggest that the universe splits into alternate timelines with every decision made. In such models, there could be infinite versions of the past, branching endlessly in parallel. These interpretations are controversial, but they open the door to an even weirder idea: that the past isn't just out there, it may be many things, coexisting in a superposition, waiting to be resolved by an act of observation. We're not saying we can build a time machine, but we're not saying we can't either. The universe is still hiding its secrets, and time, perhaps more than any other, remains the most elusive. So where does that leave us? It leaves us in a universe where time is not a flowing river, but a vast ocean. Each moment is a wave that rises and falls, but never disappears. You are not standing on a platform watching time pass. You are immersed in it, like a fish in water. Every moment you've lived may still shimmer somewhere, encoded in the light scattered across the stars, preserved in the structure of space-time. You are part of a vast mosaic, every version of you that's ever existed, stitched into the fabric of reality like threads in a cosmic tapestry. Maybe you'll never travel to the past. Maybe you'll never reach out and touch yesterday. But the idea that it still exists, quietly and eternally, in some form, whether in the geometry of space-time or the echo of ancient light, is a comforting one. So as you drift off, allow yourself to imagine that every moment of your life, every laugh, every breath, every quiet thought is still out there, somewhere, glowing softly in the cosmic dark. To continue our quiet journey into the nature of time and the past, we need to explore a concept that seems, at first, almost mystical: simultaneity. In everyday life, we assume that now is the same for everyone. If it's 8 p.m. for you, you might assume it's 8 p.m. everywhere, adjusted only by time zones. But in physics, especially under Einstein's special relativity, this is not the case. What one person considers now might be the past or future for someone else. This lack of a universal now is called the relativity of simultaneity, and it means that there is no single moment shared by the entire universe. Imagine two people, one standing still on Earth and another flying past in a spaceship at near light speed. Because of how time and space are intertwined in space-time, each observer will have a different slice of now. What's present for the person on Earth might be the past or future for the traveler. This isn't a trick of perception, it's built into the geometry of the universe. This undermines the idea that the past has truly vanished. If there's no one universal present moment, then perhaps all moments still exist, and our conscious awareness just moves through them. Now think about how strange that is. Somewhere, from a different frame of reference, your past may still be happening. To an alien far away, zipping through the cosmos, the light reaching them from Earth might show you being born. From their perspective, that might be their now. They are, in effect, observing your past as their present. But we can take this even further. There's a concept in physics called the light cone. Imagine a single event, like you snapping your fingers right now. Light spreads out from that moment in every direction at the speed of light. That spreading sphere is your future light cone. Any events inside that cone can be affected by your snap. Likewise, there's a past light cone. That's all the events in the universe that could have affected your snap. Anything whose light or influence could have reached you in time to matter. The fascinating part: anything outside those cones, events that are neither in your causal past nor future, are not definitively before or after your moment. They are elsewhere in space-time, neither reachable by nor reaching you. Their relationship to your now depends on your frame of reference. This suggests that time isn't a line, it's a web. Events are linked not by a single flowing timeline, but by the structure of their light cones. And that structure is not the same for every observer, so could the past still be out there? According to relativity, yes. From the perspective of a different observer, it might still be part of their present. This brings us to an extraordinary realization. The past is not erased. In some frames of reference, it's still active, still real. The idea of one shared timeline simply doesn't hold up. Let's shift for a moment to cosmology. The study of the entire universe. When scientists look at the cosmic microwave background, or CMB, they're seeing the oldest light in the universe. This faint glow, left over from the Big Bang, has been traveling for nearly 14 billion years. It's everywhere, in every direction, and it's incredibly uniform. The CMB is not just a snapshot, it's a direct observation of what the universe looked like long ago. And it hasn't changed. Those photons have been traveling all this time, untouched, unchanged, bringing us a message from the past. Now consider this. If we can see the universe as it was nearly 14 billion years ago, then the light from everything that has ever happened on Earth is also traveling outward. Our planet radiates light constantly. Radio signals, TV broadcasts, and even just reflected sunlight. That information is now spreading through the galaxy in a shell, 1 light year thicker with each passing year. From far enough away, and with the right tools, another civilization could detect our signals, perhaps even decode them. A TV show broadcast in 1950 might just now be reaching a planet 75 light years away. To an observer there, our past is still alive and unfolding. It's like ripples in a pond, except the pond is space-time, and the ripples are history itself. So what about the idea of reversing time? If the past still exists, could we ever travel back to it? This question leads us into the realm of general relativity, which describes how gravity works as the warping of space-time. According to Einstein's equations, it's theoretically possible to create curves in space-time that loop back on themselves, called closed time-like curves. These would allow for paths through the universe that return to their starting points in time, not just space. Certain solutions to Einstein's field equations, like the Gödel metric or rotating black holes, called Kerr black holes, contain these closed time-like curves. In theory, if one could survive the extreme conditions near such an object, you might loop back in time. But there's a problem. These structures may be mathematically possible, but they seem physically unstable. Even the slightest disturbance, like a passing photon, could cause them to collapse. And worse, they create paradoxes that physics doesn't know how to resolve. That said, the equations allow for it. And that matters. Some physicists believe the universe enforces a chronology protection conjecture, a kind of cosmic rule that prevents backward time travel. This would preserve causality and keep the timeline from unraveling into nonsense. But even if we can't go back physically, could we observe the past in other ways? This brings us back to information. In physics, information is never truly lost. Even when something is destroyed, like a log turning into ash, the information about its structure and composition still exists in the arrangement of the particles that remain. This idea was tested most famously in the black hole information paradox. For decades, physicists believed that anything falling into a black hole was lost forever. But this contradicted quantum mechanics, which insists that information must always be preserved. Eventually, Stephen Hawking and others proposed that black holes might not destroy information, but instead encode it subtly in the radiation they emit, a concept known as Hawking radiation. If black holes preserve information in this way, then perhaps every event in the universe leaves behind a trace, a kind of echo, written into the quantum fabric of reality, not just in light, but in the fundamental structure of particles and fields. Imagine the universe as a massive hard drive. Every interaction, every motion, every change is recorded, not in ones and zeros, but in the patterns of quantum entanglement and field fluctuations. In this view, the past isn't just visible via light, it's embedded in the universe itself. There's also the idea of the holographic principle. This proposes that the entire universe is like a hologram, where the information about everything inside a region of space is encoded on its outer boundary. If true, then the past might not be in the past at all. It might be encoded on the edges of space, like data on a disk, accessible not through time travel, but by reading the geometry of space itself. This is all theoretical, of course, but it shows that the idea of a vanishing past is far from certain. Let's reflect for a moment. When you remember something, a birthday, a quiet moment, a song, you're not just inventing it. Your brain is reconstructing a pattern from a stored configuration of neurons. That memory is real in a certain sense. It's a physical structure inside your mind, activated by the present. Now imagine the universe doing something similar. Every event leaves behind a kind of memory in the way particles move, in the way fields ripple, and in the light that flies outward. These are not stories we tell. They're real patterns etched into the cosmos. We might not have the tools to decode all of them yet, but the universe remembers. So where is the past? It may be smeared across the stars, drifting in waves of ancient light. It may be locked in the spin of a neutron star or the orbit of a distant comet. It may be hiding in the twisted paths of gravity or curled up in the math of spacetime itself. But it's not gone, not really, and that is both comforting and humbling. You are part of something vast, something that remembers. Every whisper, every movement, every breath you've ever taken left a trace, not just in your own mind, but in the universe itself. So even if we can't go back, if we can't open a door to yesterday, the echoes remain. The past hasn't vanished, it simply moved beyond reach, shining softly in the background, like the glow of old stars in a deep, quiet sky. As we journey deeper into the nature of time and the past, let's begin with a quiet yet profound idea. What if the universe doesn't forget? This thought may sound poetic, but in physics, it's taken quite seriously. There's a growing body of evidence suggesting that information is never truly lost, only transformed. Even when something appears to vanish, like a burned book or a collapsed star, the universe still keeps the information encoded in some form. And if this is true, it changes how we understand the past. It may not be gone. It may simply be hidden, preserved in the structure of reality, waiting to be uncovered. To better understand this, let's explore the concept of determinism. In classical physics, the universe is deterministic. That means that if you knew the position and motion of every particle in the universe at one moment, you could, at least in theory, calculate everything that has ever happened or ever will happen. The future and the past are locked in by the present. This idea goes back to Pierre-Simon Laplace, an 18th century physicist who imagined a vast, powerful intelligence, now called Laplace's demon, capable of knowing the complete state of the universe. Given enough knowledge, Laplace's demon could rewind or fast-forward reality like a film strip. Every moment, every choice, every change would be encoded in the current state of matter and energy. So, under classical determinism, the past must still exist, because the present is just the latest step in a continuous chain. Nothing is lost. It's all there, embedded in the flow. But then came quantum mechanics, and with it, a certain kind of uncertainty. At the smallest scales, particles don't behave in strictly deterministic ways. Instead of following a single path, they exist in probabilities, a cloud of possible outcomes. The famous Heisenberg uncertainty principle tells us that we can't know both the position and the momentum of a particle with absolute precision. There's always some fuzziness. This raised a serious question. If quantum mechanics introduces randomness into the universe, does that mean the past can be erased? If something happens randomly, can we trace it backward to a cause? The answer, surprisingly, is still yes, but it depends on how you look at the situation. Quantum mechanics doesn't destroy determinism, it simply changes how we define it. In many interpretations of quantum theory, like the many worlds interpretation, every possible outcome of a quantum event actually occurs, but in a different branch of the universe. So the universe doesn't pick a single future, it creates them all. This also applies to the past. Every quantum interaction leaves behind a trace, a kind of footprint that's entangled with the rest of the universe. This is called quantum decoherence. Even though outcomes seem random, they're woven into the fabric of space-time. The information isn't lost, it's just incredibly difficult to access. Let's bring this down to a more human scale. Imagine you toss a coin. In classical physics, if you knew everything about your hand, the air resistance, the spin, and the weight of the coin, you could predict how it would land. In quantum mechanics, that same coin might interact with trillions of microscopic variables: air molecules, electromagnetic fields, quantum vibrations, and those interactions create a blur of possibilities. But once the coin lands, those possibilities collapse into one result. Here's the beautiful part. The entire system still holds a record of what happened. The energy you exerted, the motion of your muscles, even the slight rise in temperature from your breath, all of it has consequences that ripple outward. Every movement, however small, alters the world in tiny but measurable ways. So in a very real sense, your past actions are preserved, not just in memory or in history books, but in the molecules of the air, in the vibrations of the ground, in the quantum entanglements of nearby particles. Nothing is forgotten, nothing is truly gone. This takes us to the idea of quantum records. In theory, if we had a device sensitive enough, we could trace back the history of a single particle, unraveling its path by reading the influences left behind. This kind of backward reconstruction has been proposed in quantum experiments involving weak measurements, where scientists try to gather information about a particle without fully disturbing it. In these experiments, researchers have been able to make statistical inferences about the past behavior of particles, what paths they likely took, and where they likely came from, without directly observing them. It's like reading footprints in the snow. You can't see the traveler, but you know they were there. Now imagine expanding that idea to the whole universe. Every interaction, from the birth of stars to the flicker of a candle, creates a cascade of quantum records. These records are fragile, scattered, and tangled, but they are real. Theoretically, the past still exists as a ghostly presence in the state of the present. But what would it take to read these records? Here's where we encounter the limits of technology and imagination. To reconstruct the past from quantum information would require impossible precision, something beyond the reach of current or even foreseeable tools. It's not about capturing memories like a video camera. It's about decoding the ultrafine structure of quantum interactions across the entire cosmos. Still, the idea lingers. Somewhere, written into the spin of particles and the dance of atoms, is the story of everything. Even time itself might be emergent, not a basic feature of reality, but something that arises from quantum entanglement. Some physicists propose that space and time are not fundamental ingredients of the universe, but side effects of deeper relationships between quantum bits of information. In this view, time is a consequence of how things are entangled, not a container in which things happen. If that's true, then the past may be more than just still out there. It may be the structure of the present. Let's now turn to gravity. Gravity, as described by general relativity, doesn't just pull objects, it bends time itself. Near a massive object like a planet or a black hole, time slows down. This isn't hypothetical, it's measurable. GPS satellites must account for gravitational time dilation to stay accurate. Now imagine being near a black hole. Time would slow to a crawl for you while the rest of the universe raced ahead. From your perspective, the outside world would seem to speed up, but from the outside, you'd appear to freeze in place. If you could survive the edge of a black hole, called the event horizon, you might glimpse the universe's future unfolding in fast motion. And conversely, to someone far from the black hole, you would seem suspended in the past. This strange relationship between time and gravity has led some theorists to suggest that black holes might preserve time itself. Not just information, but moments, held in the warped folds of space-time. There's even speculation that the interior of a black hole might encode a history of everything it swallowed. Again, we don't yet know how to test these ideas, but they point to a powerful conclusion: time is malleable. It can be bent, stretched, even frozen. And if time is something that can be shaped, then perhaps it's also something that can be stored. So where does all of this leave us? We began by asking a simple question: is the past still out there in the universe somewhere? We've seen that under the block universe theory, it is, eternally, silently existing in a four-dimensional structure. We've explored how light carries images of the past across space, turning telescopes into time machines. We've learned that quantum mechanics preserves information, and that even in the uncertainty of particles, the past leaves fingerprints. We've ventured into relativity, where time is not a river, but a landscape, and where your now is not the same as someone else's. In every direction, the evidence whispers the same truth. The past does not vanish. It echoes, it ripples, it radiates. It's encoded in light, in gravity, in quantum spin, in the bending of space itself. Maybe we can't touch it, maybe we can't return to it, but the past surrounds us, hides within us, and shapes the present in ways we're only beginning to understand. As you sit in this moment, remember, this moment too will soon be the past, but it will not be gone. It will become part of the universe's memory, etched in light, scattered in air, carried forward by the gentle unfolding of time. And perhaps, just perhaps, it will be visible again someday, in some strange corner of the cosmos, to some quiet observer, far from here and far from now. To deepen our understanding of whether the past is still out there, we need to examine a rather curious idea from physics, one that blurs the line between memory, measurement, and reality itself. The idea that the act of observation not only reveals, but helps define the very nature of time. Let's begin with one of the strangest discoveries in modern science, the double-slit experiment. This experiment, in its simplest form, involves firing individual particles, like electrons or photons, at a barrier with two slits. Behind the barrier is a screen that detects where the particles land. If you fire them without observing which slit they pass through, they create an interference pattern, suggesting each particle behaves like a wave, passing through both slits at once, interfering with itself. But if you set up a detector to observe which slit the particle goes through, just observe, not interfere, the interference pattern disappears. Instead, the particles behave like little marbles, passing through one slit or the other. The very act of measuring collapses the wave function. The system behaves as if it knows it's being watched. Now here's the twist. In some variations of the experiment, known as the delayed choice version, scientists can decide whether or not to observe the path after the particle has passed through the slits, but before it hits the screen. And yet the interference pattern, or its absence, still changes depending on what choice is made. It appears as if the particle's past behavior, the choice to act like a wave or a particle, depends on a decision made in the future. It's as though reality waits until the last possible moment to determine what happened. This challenges our intuition. We assume that the past is fixed, that what has happened is unchangeable. But quantum mechanics suggests a deeper level of fluidity. The universe, at its most fundamental level, does not settle into a single history until an observation is made. This doesn't mean you can go back and rewrite history, but it does imply that what we call the past may not be as solid or determined as we think. In the quantum world, the past and the future are entangled. They're part of the same whole. So where does the past go when no one is looking? Does it collapse into a single outcome? or does it remain in a haze of probabilities? Many physicists believe that quantum decoherence offers an answer. When a quantum system interacts with its environment, it becomes entangled with it. This entanglement spreads rapidly, and soon all possibilities except one fade into irrelevance for any practical measurement. This is how the classical world we know emerges from the quantum world, through loss of coherence. But here's the important point. The information about those other possibilities isn't destroyed. It's simply no longer accessible. Like a trail covered in fresh snow, the path is still underneath, but invisible. This idea supports the notion that the past remains, at least in some form, embedded in the quantum state of the universe. It's there, not as a memory, but as part of the deep structure of reality. Let's now take a softer detour into the role of memory itself. Human memory is, in many ways, a personal time machine. We remember not just events, but feelings, textures, voices, and sounds. These are stored in the brain as patterns, complex networks of synapses and firing neurons. When you recall something, your brain doesn't replay a recording. It rebuilds the experience using traces left behind by your senses. But memory is not perfect. It fades, distorts, and often changes with time. This is because memory is biological, not physical. It's subject to the same entropy that affects everything else. Over time, the patterns that encode your memories weaken or transform, and yet your memory is real. It exists as a configuration of matter and energy. It is a physical state in your brain, tied to a specific chain of events. In that sense, it is a form of preserved past, a miniature echo inside your mind. Now let's consider something larger, the Earth itself as a recorder of time. Fossils, tree rings, glacier cores, sediment layers. These are all forms of natural memory. They contain information about ancient climates, extinctions, the oxygen content of the atmosphere, even the orientation of the magnetic field over millions of years. Scientists have used these records to reconstruct the distant past, not just in broad strokes, but in remarkable detail. We can know how much rainfall fell in a given year thousands of years ago, or what kind of pollen drifted through the air. These are not guesses, they are empirical facts, etched into the planet itself. In a way, the Earth is a living archive. Its rocks and rivers remember. Its mountains tell stories. Its ice holds breath from ancient skies. The past is not gone, it's just locked in place. But even this is limited. The Earth's surface changes. Tectonic plates shift, erosion grinds down monuments and records. Time acts as both preserver and destroyer. So we must look further out. Light, again, offers a clue. As we've said before, light travels at a finite speed. This means we can, in principle, observe the past directly by capturing ancient photons. But it also means something stranger, that the now we experience is a kind of illusion. When you look at someone across the room, you're seeing them as they were a few nanoseconds ago. When you observe the moon, you see it as it was 1.3 seconds ago. The sun, 8 minutes ago. The nearest star, over 4 years ago. In fact, there is no universal now across space. There is only the time it takes for light to travel between 2 points. So when we observe the universe, we're always observing history. This stretches even further. Imagine a spaceship 65 million light years away, pointed directly at Earth with a powerful telescope. If the observer had the ability to decode light in exquisite detail, they would be watching Earth as it was when the dinosaurs vanished. For them, that is the present. So the past is out there, objectively, measurably, carried in the form of light. It's not philosophical or speculative. It's visible, in principle, to any being in the right place at the right time. This naturally leads to a more profound possibility that the universe is not just a container of events, but a kind of computation. Some physicists and philosophers believe the universe functions like a giant quantum computer, where every interaction is a calculation and time is simply the running of a cosmic algorithm. In this model, past, present, and future are not absolute. They are states of a process. The state you occupy now includes within it all the information from previous states, encoded in the current arrangement of matter and energy. This perspective aligns with the idea that the past is preserved, not as separate moments, but as code embedded in the structure of reality. If you could rewind the computation with perfect fidelity, the past would unfold identically. It hasn't been lost, it's still there, held in the logic of the whole. We can also consider the concept of spacetime crystals, structures proposed in theoretical physics that repeat not just in space, but in time. These time crystals are still being explored in quantum experiments, but the idea is striking that certain systems may exhibit time-based patterns that never decay. If these patterns exist, they would challenge our assumptions about entropy and permanence. They would suggest that some kinds of motion, some dances of particles, could repeat forever, unchanged, a form of temporal memory built into matter itself. So perhaps the past is not a place, but a rhythm, a pattern that continues to echo beneath the surface of everything. One final thread to consider: the role of consciousness. We experience time as a sequence. Our minds move forward, one thought, one heartbeat at a time. But we do not experience all time. We only experience now. Why? Some neuroscientists believe the brain constructs the illusion of time through a complex integration of sensory inputs and memory. The sense of continuity, the flow from one moment to the next, is not a feature of reality, but of perception. This opens a strange door. If consciousness is what creates the experience of time, then maybe time is less about external events and more about how we organize them. In other words, the past might not feel past unless something experiences it that way. In this view, the past exists objectively, in light, in atoms, in information, but it only becomes past when we separate it from the now. So is the past still out there? From what we've explored so far, the answer seems to be yes. Yes, in the light crossing space, carrying ancient images of stars, galaxies, and even Earth itself. Yes, in the entangled particles and quantum patterns that preserve the traces of everything that has happened. Yes, in the structure of space-time, where all events may coexist eternally in the cosmic block. Yes, in fossils and ice cores and memories, in neurons and tree rings and magnetic fields. The past surrounds us, hides beneath us, and glows above us. It does not vanish, it transforms. And though we may never walk through it, we can sense its presence. In the stars, in our science, and in the quiet awe we feel when we realize that we are part of something vast, slow, and beautifully mysterious. To reach the heart of our question, whether the past is still out there, we must now venture into a deeper realm of time itself. Not just how time is structured or how it's observed, but how it might be created. Let's begin by asking something radical. What if time is not fundamental? This idea, while counterintuitive, is gaining traction in theoretical physics. According to several modern theories, time may not be a basic building block of the universe like matter or energy. Instead, it could be a byproduct of more fundamental processes, emerging from quantum interactions, entanglement, or the organization of information. If this is true, then the entire notion of the past being gone becomes questionable. Because if time is not real in the way we experience it, then our distinction between past, present, and future might be artificial, an illusion, a convenience of biology and perception. Let's go back to the idea of the block universe. In this model, time is like space. It's a dimension that can be measured, but not one that necessarily flows. All moments exist simultaneously, fixed in the four-dimensional structure of space-time. You are not moving through time like a train on a track. Instead, you are a four-dimensional being, extending through time just as you do through space. In this view, your childhood is just as real as your current moment. It's simply located at a different coordinate in space-time. You don't remember it because your consciousness, your sense of now, is focused on this particular slice, but the slice from your childhood still exists. It's not deleted, it's not destroyed, it's just not where your awareness currently is. This concept becomes even more compelling when we consider how gravity affects time. According to general relativity, the stronger the gravitational field, the slower time flows. This has been measured directly. Clocks placed at different altitudes tick at different rates. In extreme environments, like near a black hole, time can slow so much that a few minutes near the event horizon could equal years elsewhere. So now imagine two observers. One floats far from any gravitational pull. The other orbits a supermassive black hole. After a few hours, the one near the black hole returns and finds that decades have passed for the other. To the distant observer, their friend has leapt into the future. But from the perspective of the one near the black hole, they only experienced a few moments. This isn't science fiction. It's been confirmed experimentally and is consistent with all our current models. Time is not fixed, it's relative. So what does this tell us about the past? It suggests that time is local, not universal. It behaves differently depending on where you are and how fast you're moving. This implies that there's no single timeline we all move through. Instead, there are countless overlapping timelines, all flowing at different speeds and in different directions depending on the observer. And if that's true, then our definition of the past depends entirely on context. What you consider the past might still be unfolding for someone else. What feels like a memory to you could be an active moment in another frame. The past isn't a closed door. It's a location on a map of space-time, one that others may still be walking through. Now let's consider something even more abstract, the possibility that time arises from entanglement. Entanglement is a quantum phenomenon in which two or more particles become linked in such a way that the state of one instantly affects the state of the other, no matter how far apart they are. It defies classical logic and has been confirmed countless times in laboratory experiments. But some physicists, like those studying the ADS, CFT correspondence, or emergent gravity, have proposed that space-time itself may arise from networks of entangled particles. That is, space and time are not the foundation of reality, they are consequences of quantum information. In this model, time doesn't exist until entanglement structures it. It's not something you travel through. It's something created by relationships between quantum systems. This theory implies that what we experience as time, a before and an after, a cause and an effect, is not built into the universe. It emerges as a side effect of how complex systems organize themselves. If that's true, then the past doesn't go anywhere. It simply becomes part of the entanglement web. Each moment is connected to the next by the informational threads of quantum states. Pull on one, and the vibration is felt by others. There's no deletion, no erasure, only complexity building upon complexity. So how does this square with our experience of forgetting, of time slipping away, of things decaying, disappearing, or dying? Enter entropy. As we've discussed, entropy is a measure of disorder. The second law of thermodynamics tells us that entropy in a closed system will always increase. This gives time its direction, from order to disorder, from low entropy to high entropy. When you drop a glass, it shatters. The energy that once held its shape becomes dispersed. You can't easily put it back together, not because it's impossible, but because it would require a level of precision and energy that's practically unattainable. But here's the key: the information about the intact glass isn't gone. It's just scrambled. The pieces, the air molecules, the sound waves, they all contain traces of what happened. The past event lives on in the configuration of the present. Entropy doesn't destroy information, it diffuses it. This principle is central to the modern understanding of black holes. For years, physicists believed that anything falling into a black hole was lost forever, violating the principle of information conservation. But Stephen Hawking and others later proposed that black holes emit radiation, now called Hawking radiation. And buried in this radiation, they argued, is the information about what fell in, coded in a way we don't yet fully understand. This has led to the holographic principle, the idea that all the information contained in a volume of space can be encoded on its boundary. If the universe obeys this principle, then everything that happens inside it, including the past, is written on the edges of reality, like cosmic graffiti. You can't always read it, but it's there. Now let's bring this closer to home. Consider a moment from your past, something quiet and personal. A walk in the evening, a conversation that lingered, a glance that meant something. That moment created ripples. Your voice stirred air molecules. Your footsteps pressed against the ground. Photons bounced from your skin, scattered, and left on journeys that may never end. All of that is part of the universe now. The moment may seem gone, but the traces remain, subtle, diffused, real. In a very literal way, the past is not behind you. It is beneath you, around you, and even within you. We are built from stardust, but also from memory. Not just neural memory, but physical memory. Atomic memory, cosmic memory. Each of us is a record, a snapshot of billions of years of evolution and interaction. And this leads us to one last idea for today, that time, and therefore the past, is not something that flows. It is something that's grown. In the thermodynamic view, time is a record of increasing complexity. The universe started in a low entropy state, a smooth, hot, dense condition we call the Big Bang. Since then, it has become more structured, more intricate. Galaxies formed, planets coalesced, life emerged. Each of these steps didn't erase what came before. They layered upon it. Like rings in a tree or layers of sediment in a canyon, the present contains the past. Not as memory, but as foundation. You are the result of everything that has ever happened. Every atom in your body was forged in a star. Every word you speak rides on waves shaped by ancient air. Every heartbeat is a continuation of a chain that began long before you were born. The past isn't somewhere else. It is here. Not just in ideas, not just in history, but in substance. In the hydrogen in your blood, in the carbon in your skin, in the calcium in your bones. You are walking in evidence that the past endures. And though we may not have a machine to visit it, we are always touching it, breathing it, becoming it. So when we ask, is the past still out there in the universe somewhere? We are really asking, what is time? What is memory? What is permanence? And the answer, if we listen closely to the silence of the stars, might be this. The past does not go. It stays. Let us begin tonight's continuation with a stillness, a quiet understanding that time, while elusive, leaves imprints everywhere. These imprints are not metaphors. They're measurable, physical, and undeniable. So far, we've explored time through the lenses of relativity, quantum mechanics, light, and memory. But to go deeper, we must now look at time through symmetry, and how the laws of physics themselves may hint that the past never truly disappears. In physics, symmetry often reveals what is allowed and what is conserved. There's a fundamental symmetry in many of the equations of physics. Time symmetry. Most physical laws are time reversal invariant. This means that if you took a video of a process governed purely by those laws, say, two particles colliding, and played it backward, the reversed motion would still be valid under the laws of physics. If you watch a rock fall in reverse, it looks like it's jumping up. Both directions are allowed in Newton's laws and in most quantum field theories. The math doesn't care which direction time flows, it just works. So why then do we experience time as one-directional? Why does the past feel fixed while the future feels open? The answer, as we've touched on before, lies in entropy. While the laws of physics are reversible, the conditions of our universe are not. The universe started in a state of extremely low entropy, remarkably ordered. And from there, entropy has only increased. Entropy provides what's known as the arrow of time. It's not a law, it's a tendency. It's not about what can happen, but about what does happen. Left alone, systems tend to become more disordered over time, and that one-way march gives rise to our experience of time flowing. But, and this is important, while the arrow of time affects how we perceive and interact with events, it does not eliminate the past. It only marks the direction in which new information is generated. The past doesn't evaporate, it becomes encoded, in ashes, in echoes, in the cooling structure of the cosmos. And if time's arrow is merely a result of initial conditions, then perhaps all moments, past, present, and future, are equally real, equally existent. The direction we face in time may be no more special than the direction we face in space. Now let's shift our gaze to a more profound question. Is time even continuous? Most of us think of time as a smooth flow, like a river that never stops. But in theoretical physics, some models suggest that time may be discrete. That is, it comes in tiny, indivisible units, like pixels in an image or notes in a melody. If true, then each moment of time would be like a frame in a cosmic film reel. One such approach is called loop quantum gravity. This theory proposes that space and time are quantized, that there is a smallest possible unit of space and of time. You cannot divide a second endlessly. Eventually, you hit the smallest possible tick of the universe's clock. In such a universe, every moment is distinct, frozen, defined. And if moments are discrete, they can be preserved. Each frame could, in principle, exist forever, unchanged. Our experience of time moving forward would simply be our consciousness skipping from one frame to the next. But the previous frames would remain, just like a sequence of film images in a projector that's no longer running. This raises a fascinating thought. Maybe the past is still out there, not just as a possibility or as an effect, but as a static structure, an individual unit of space-time, preserved within the total geometry of the universe. Some physicists refer to this as the museum of moments. All moments exist, but we only ever experience one at a time. Our consciousness is like a flashlight scanning over frozen exhibits. Each moment lit up, experienced, and then passed over, though never erased. If this idea is even partly correct, then the past isn't just out there, it still is. Now consider a theory from cosmology known as eternal inflation. According to this model, our universe is just one bubble in a vast multiverse, where inflation, an incredibly fast expansion, creates new pocket universes all the time. Each of these universes may have different laws of physics, different constants, different timelines. In some of these universes, time might not exist at all. In others, it might flow differently, or even backwards. This cosmic perspective reframes our question in a remarkable way. If the multiverse is real, then our past may still be happening, not just in our own universe, but in a near-identical bubble where the clock ticks just slightly slower, or slightly faster, or loops in circles. And even if we can never reach these places, the information is staggering. Our past may be infinitely replicated, infinitely varied, and infinitely preserved across a limitless landscape of universes. But we don't need to look to other universes to find stunning examples of preservation. Let's return for a moment to light. Consider again that light carries information. The light from a person walking across a field, from a star being born, from a city turning on its lights at night. All of this light travels outward, forever. The photons scatter, fade, and stretch, but they do not vanish. They form a growing shell of history, an expanding sphere that moves outward at the speed of light. If you had a telescope with infinite sensitivity and you are 100 light years away, you could, in theory, see Earth as it was 100 years ago. Not just the surface, but specific photons reflecting off buildings, clouds, oceans, even people. This isn't fiction, it's physics. Of course, the odds of collecting enough scattered photons to rebuild a high-resolution image of the past are astronomically low. But the point is, the information still exists. It's out there, carried by light, waiting. Now let's go even more speculative. Some physicists have proposed that time may be a side effect of consciousness. This is not to say that time doesn't exist outside of us, but rather that the experience of time, of one moment following another, is something created by awareness. In this view, the universe may contain all moments at once, but without a conscious observer, there is no before and after, no causality, no change. It's all static, like a painting, infinitely rich, but motionless. What animates that painting, what breathes sequence into stillness, is the act of perception. Your brain processes inputs in patterns. It compares the current state to the one before. It creates the illusion of flow by stitching frames together, like a movie. You are the projector and the film. It's the universe. This raises a deep question. If a tree falls in a forest and no one is there to hear it, does it make a sound? The scientific answer is, it creates pressure waves in the air. But sound, as we know it, is a perception. Similarly, if the past exists but no one remembers it, is it still the past? If no mind ever revisits it, does it matter that it endures? Here, we are at the edge of physics and philosophy. Yet even here, the clues point to persistence. The past leaves footprints, not metaphorical ones, real ones. In the arrangement of atoms, in the flow of energy, in the weak radiation of an ancient fireball we call the cosmic microwave background. The universe is not forgetful. It carries its past forward. Even in death, stars leave memories. White dwarfs, neutron stars, black holes. And even black holes may not be silent tombs, but recorders, preservers of the things they've consumed through the slow evaporation of Hawking radiation. What then are you, a being made of past, constructed by history, assembled from stardust that once glowed in the hearts of ancient suns, animated by information carried through eons. You are a pattern, highly ordered, full of memory, and tethered to a timeline that stretches back to the very beginning. You are, quite literally, living evidence that the past is not gone, and though we cannot go back, though we cannot climb into the frame we've left behind, we carry it with us. In our molecules, in our thoughts, in the language we speak, and the dreams we share. The past does not fade. It radiates like a soft afterglow, like ripples in space-time, like light that has yet to reach its distant destination. Somewhere, 100 light years away, a photon reflected from your face is still traveling. In 1,000 years, it may brush past a distant world. In 10,000, it might scatter in a nebula. In 1,000,000, it may still exist, a whisper from Earth carrying the shape of your presence forward into the night. So yes, the past is still out there, not in mystery, in motion, not in fantasy, in physics. And the deeper we look, the more we realize time doesn't wash things away. It layers them, builds upon them, carries them. As we continue our quiet journey into the nature of time and the mystery of the past, it's worth slowing down to ask something deeply personal. Why do we want the past to be out there? What draws us to this question, not just as scientists, but as human beings? Perhaps it's because we sense, even without precise language, that the past isn't truly gone. We feel its presence in memories, in relics, in echoes of moments that shaped us. We reach for it with photographs, letters, ruins, even nostalgia. But while emotion may stir the question, science gives us surprising tools to answer it. Let's revisit one of the most powerful ideas in modern physics. Information never disappears. This principle, often traced through quantum mechanics and black hole thermodynamics, is not just theoretical, it's foundational. In quantum theory, the evolution of any system is governed by equations that are reversible and conserve information. Even if the form changes, the content remains. When particles interact, when they bounce, combine, decay, or scatter, they do so in ways that preserve the underlying information about their states. The challenge isn't that the past is lost, it's that the information is scrambled into complexity. Think of a jigsaw puzzle. Once assembled, the image is clear. But if you throw the pieces into the air and let them fall, the picture disappears. Not because the pieces are missing, but because the arrangement no longer reveals the whole. The information is still there, just disordered. This concept applies to everything: a fire-consuming paper, a tree falling in the forest, even your thoughts dissolving into sleep. Physics tells us that the information is not erased. It's just entangled, scattered, encoded in forms beyond easy reach. And yet, theoretically, if you could track every interaction, every vibration, every quantum state, you could rewind the universe and reconstruct the exact state it was in at any prior moment. You could, in essence, read the past directly from the present. Now consider a different kind of information. Gravitational waves. These are ripples in the fabric of space-time, predicted by Einstein and first directly detected in 2015. They're produced by massive objects accelerating, like two black holes spiraling into one another. When gravitational waves pass through the Earth, they distort distances by tiny amounts, fractions of the width of a proton. But incredibly sensitive instruments, like LIGO and Virgo, have learned to detect these distortions. Why does this matter to our question? Because gravitational waves carry history. They are literal vibrations of space-time caused by events that happened millions or even billions of years ago. When we detect a wave today, we are hearing a cosmic echo, a message from a past that still radiates energy into the present. These waves aren't like radio signals. They aren't distortions of air or light. They're distortions of the very geometry of reality. When a gravitational wave passes through you, your body stretches and compresses. Not enough to feel, but enough to measure. And that means the universe itself remembers. It remembers the collision of stars, the spiral of galaxies, the trembling of space-time when massive bodies twist and merge. These events aren't lost. Their effects propagate endlessly, quietly, invisibly, but always forward. We are beginning to tune into these vibrations, and the more we listen, the more we find that the past isn't silent. It sings in deep, slow frequencies. It resonates. And if the universe resonates, then it keeps memory not just in matter, not just in light, but in space itself. Now let's return to a haunting idea from quantum physics: retrocausality. Retrocausality is the suggestion that future events can influence the past. It sounds impossible, but some interpretations of quantum mechanics allow it. Consider the quantum eraser experiment. It builds on the classic double-slit setup, with entangled photons. In one version, you can choose to erase or retain information about a particle's path after it has already been detected. When you erase the information, an interference pattern reappears, as if the photon had behaved like a wave the entire time. When you preserve the witch path data, the interference pattern disappears. Here's the strange part: your future choice seems to determine what the particle did in the past. This doesn't mean we can send messages into the past or alter it in the Hollywood sense, but it does mean the boundaries between past and future are less rigid than we once believed. In quantum entanglement, causality can be non-linear. Information is shared instantly, across space, without delay. The universe behaves not like a sequence of dominoes, but like a vast interconnected web, where everything influences everything else, not just forward, but across. So if the present can influence the past, at least in a quantum sense, then the past must still be part of the whole, still accessible, still connected, still there. Let's shift now to the role of measurement. When we measure a quantum system, we collapse a superposition of possibilities into one definite state. Before measurement, the system exists in all possible states simultaneously. After measurement, it takes on a single form. But here's the subtle point: the system only seems to collapse. In some interpretations, especially the many worlds interpretation, there is no collapse. Instead, all outcomes happen, but in different branches of the universe. What we see as a definite past is just one path through a vastly branching tree. If true, then the past you remember is only one of many possible pasts. The universe doesn't discard the others, it keeps them. They continue, diverge, evolve. This is the quantum multiverse. Not a place of fantasies, but a cold, mathematical structure. Every quantum interaction splits the universe into multiple versions, each equally real. The version you inhabit is just one thread in a vast tapestry of alternate pasts, all branching from a common trunk. If every past exists in some form, then the past is not just out there. It's everywhere, you just happen to be inside one version. Another perspective comes from causal set theory, a lesser-known but fascinating approach to quantum gravity. In this model, space-time is made of discrete elements, like atoms of time. Each element is linked to others in a network that defines causality. What can influence what? The result is a space-time that grows, not a static block, but an expanding web of cause and effect. The past doesn't vanish. It becomes part of the structure, unchanging, immutable, always present. The present builds upon the past like a city built on ancient ruins. Even if we pave new roads, the foundation remains. We stand upon it, even if we do not see it. This idea has something deeply comforting in it, that your life, your choices, your memories are not just fleeting sparks, but real contributions to the architecture of the universe. The past is not behind us, it is beneath us, holding us up. We can't leave this discussion without returning, briefly, to light. Light is the fastest thing we know. It moves at 299,792 kilometers per second, about 186,000 miles per second. Nothing can overtake it. And because of this, light from past events continues to race outward, undisturbed, into deep space. If you shine a flashlight into the sky, some of those photons will keep going. Forever. They won't come back. They won't stop. They will carry the shape of your gesture, the angle of your hand, the flicker of your decision, into the black. Imagine this. Somewhere, 1 billion years from now, one of those photons might land on a distant world. It may scatter off a rock, or it may be absorbed by the eye of a being you'll never meet. And in that instant, your past becomes their present. You won't know, but it will happen. In this way, the past doesn't just linger, it travels, it touches, it arrives. That's the wonder of physics. It takes something poetic and makes it literal. The light from your childhood still moves outward. The photons from the birth of the Earth are still flying. The radiation from the Big Bang still bathes the universe, cooled, stretched, but present. So when we ask, is the past still out there in the universe somewhere? We are not chasing a fantasy. We are describing the world as it is. The past echoes in light, resonates in space, twists in gravity, encodes in atoms, branches in quantum fields. So far, we've uncovered a vast tapestry of evidence, theory, and reflection suggesting that the past, far from being gone, continues to exist in many subtle but real forms. It is carried in light, encoded in quantum states, stretched across the expanding universe, and entangled within the very structure of reality. But now, let us ask a slightly different question. If the past still exists, can it ever be retrieved? This is not about time travel in the science fiction sense. We are not talking about stepping into a machine and physically returning to another era. That remains, for now, outside the boundaries of real physics. But could there be a way, however indirect, however subtle, to observe, reconstruct, or decode the past using physical principles? Let's start with the idea of reversible computation. In classical computing, many operations discard information. When you perform a calculation on a regular computer, the result is often saved, but the intermediate steps are lost. The system generates heat, entropy, as a byproduct of erasing data. But in reversible computation, every operation is logically reversible. No information is ever truly discarded. If you had perfect access to the system and its rules, you could reverse the entire chain of operations and return to the initial state. This has profound implications in physics. If the universe behaves like a reversible computer, then the present state of the universe contains all the information necessary to recover the past. It's not that the past has vanished, it's that it has been transformed, scrambled into the current moment. Of course, in practice, this is staggeringly complex. The number of particles, the depth of interactions, and the chaos of thermodynamic processes make reverse engineering the universe nearly impossible. But not in principle. In principle, the past can be revealed. That leads us to a concept known as Laplacian determinism. In the 18th century, Pierre-Simon Laplace imagined a theoretical intellect, now called Laplace's demon, that knew the precise position and momentum of every particle in the universe. With that knowledge, it could predict the future and retrodict the past with perfect accuracy. Today, quantum mechanics complicates this picture. The Heisenberg uncertainty principle tells us we cannot know both position and momentum exactly. The universe isn't a clockwork machine, it's probabilistic, and yet, even in a probabilistic system, the idea remains that the current configuration carries with it the fingerprints of everything that came before. If we had infinite knowledge and infinite precision, we could reconstruct the past from the present, like unraveling a massive cosmic equation. This brings us to something very real: digital reconstruction. Right now, scientists are developing algorithms to reverse engineer past events from present data. In paleoclimatology, for example, ice cores are analysed to reconstruct ancient temperatures, atmospheric compositions, and climate cycles from hundreds of thousands of years ago. In astrophysics, the cosmic microwave background, a faint glow from the early universe, is studied in exquisite detail to understand how matter and energy behaved in the first few 100,000 years after the Big Bang. And in Earth's geology, sediment layers, tree rings, and radioactive isotopes are read like a library of the past. These are not guesses, these are measurements. These reconstructions are physical resurrections of time. So when we ask whether the past is gone, science answers with a quiet but powerful no. The past is not lost, it is encoded in data, in structure, in motion. The challenge is not existence, but extraction. Let's take a moment to explore a truly staggering example: light echo mapping. When a bright light source, like a supernova, explodes in space, it can illuminate clouds of gas and dust far away. The light travels outward in all directions, and some of it bounces off these cosmic mirrors and eventually reaches us later than the direct light did. By analysing these reflections, these light echoes, astronomers can literally reconstruct what the explosion looked like from different angles and times. It's as though the universe created a hologram of the past, written in starlight and stored across space. This isn't theory, this has been done. In 2008, scientists observed light echoes from a supernova that exploded in the 16th century, SN 1572, also known as Tycho's supernova. Though the event occurred over 400 years ago, its scattered light was still bouncing around in the interstellar medium, carrying information about the original event. By analysing the light echo, scientists could examine the chemical composition, speed, and even asymmetry of the explosion, centuries after it occurred. They didn't need to go back in time. The past had come to them on beams of scattered light. If you ever needed proof that the past still exists in the universe, there it is: light echoes, cosmic memory, recorded in dust. Now let's look inward. Inside your own body, there are traces of the past so ancient that they stretch back beyond civilization. Your mitochondria, tiny organelles in your cells that help produce energy, carry DNA that comes almost unchanged from your maternal ancestors. Every cell in your body holds a record in its genome of survival, migration, adaptation, and memory. You are a vessel of biological history. But it doesn't end there. The calcium in your bones was once part of stars. The iron in your blood was forged in the cores of supernovae. You are built from atoms billions of years old, arranged by a process that carries information forward, not just chemically, but structurally. In the very shape of your hands, in the rhythm of your heartbeat, in the sensitivity of your eyes, there are echoes of events you never witnessed. Evolution is not just change, it is conservation of form, inheritance of memory. Even your breath contains molecules that were once exhaled by ancient trees, extinct animals, and forgotten ancestors. The air is not clean, it is full of history. So when we ask where the past has gone, we must also ask, how can it be gone when it's still within us? Let's take a short pause for a strange thought experiment. The perfect observer. Imagine a being who could monitor every particle in the universe continuously for all time. To such a being, nothing would ever be forgotten. The past, for them, would not be a memory. It would be accessible. Not through time travel, but through measurement. We are not such beings, but physics hints that the information does not vanish. It's stored, scattered, encoded. It's just far beyond the grasp of our instruments. One day, perhaps, we will learn to read the past in finer detail, like archaeologists of spacetime, uncovering not just ruins and fossils, but entire moments, preserved in the quantum hum of reality. Now consider a final image, the shadow of Earth on the Moon. Every night, the Earth casts a shadow in space. It sweeps across the lunar surface during eclipses. That shadow carries information about position, orbit, tilt, motion, and it has done so for billions of years. Long before humans stood on the Moon, that shadow passed silently over the dust, unseen, unmeasured, but real. And now we have measured it, studied it, predicted it to incredible precision. By understanding the shadow, we understand the light. By mapping the present, we resurrect the past. So what is the universe, really? It is not a film strip running forward. It is a library of motion, a field of memory, a living fossil of change. Each moment is not erased by the next. It is absorbed, carried forward, written in light, locked in atoms, encoded in motion. And though we may forget, though our minds are soft and our memories fade, the cosmos does not forget. It remembers everything. Tonight we come closer to the edge, the quiet frontier where science touches philosophy and physics bends gently toward meaning. We've walked through time's illusions, the mechanics of memory, the cosmic preservation of light, and the whispers of quantum entanglement. But before we reach our conclusion, we must look at time from one final, profound angle. What if time is not something we move through, but something we create? This idea that time is emergent, not fundamental, is gaining ground in some of the most cutting-edge theories in physics. It's not just that our perception of time is a construct, but that time itself might not exist at the deepest level of reality. Let's consider something from quantum gravity, the Wheeler-DeWitt equation. It's a proposed unification of quantum mechanics and general relativity. But there's a catch. It has no time variable. The most comprehensive equation we have for describing the entire universe at the quantum level doesn't include time at all. That's not an oversight, it's a clue. It suggests that time may not be a built-in feature of the universe. Instead, it may arise from other variables, specifically from the way quantum systems become entangled, or how matter arranges itself at large scales. In this view, the universe isn't evolving through time. Instead, it's composed of a vast configuration space of all possible states, what's called superspace. Every possible moment, every possible outcome already exists. What we experience as the flow of time is simply our mind navigating from one point in this space to another. If time is emergent, if it's something we construct through interactions, then the past is not something that was and is now gone. It is just another coordinate in this configuration space, still existing, still part of the whole. That might sound abstract, so let's ground it in something more intuitive, your own experience of time. Have you ever noticed how time seems to slow down during moments of intense emotion? Or how it seems to vanish when you're absorbed in something you love? Or how, when remembering a vivid event, it feels almost like you're there again? These aren't just tricks of memory. They're evidence that time is not a single stream flowing outside us, but a pattern constructed inside us. Our brains stitch together experiences into a sequence. That sequence is what we call time. But here's the beautiful part. That sequence is not fixed. It's editable, reorderable. Memory is not a camera, it's a recreation. Every time you recall a memory, your brain rewrites it slightly, integrating new information, emotional context, and meaning. So what if the past is not just preserved in physics, but in consciousness? Not as a static archive, but as an active, living structure. A set of possibilities that your mind continuously refines. You don't remember the past, you reconstruct it. And that act of reconstruction makes the past real again, if only for a moment. Let's return briefly to relativity. Einstein's theory doesn't say time is an illusion, it says it's relative. There is no universal now. What you call the present is not the same as someone else's present, especially if they're moving quickly or in a different gravitational field. This leads to a fascinating consequence. There is no universal way to divide the universe into past, present, and future. What's in the future for you might already be in the past for someone else. So what does that mean? It means the division between past and present is not absolute. It's not fixed by nature. It depends on the observer. And that means, in a deep sense, the past still exists, just not from your point of view. From another perspective, perhaps from another galaxy, in another gravitational frame, your childhood is still happening. Your first steps, your first words, your first heartbreak. They are real, just elsewhere. This isn't poetry, this is a consequence of space-time geometry. And now, let's visit perhaps the most profound concept in all of this. The universe doesn't forget. Earlier we talked about how information is preserved, but now let's focus on a deeper truth. The universe is a memory machine, not like a human brain, not like a computer, but like a perfect recorder, one that never stops running, never misses a frame, and never deletes a moment. You see, everything that happens leaves a mark. A photon scattered, an atom displaced, a gravity wave rippled. Nothing in nature happens in isolation. Every action, every choice, every breath sends a cascade of changes through the fabric of space-time. Even if those changes are small, even if they're undetectable by us, they're real, permanent. If you wave your hand through the air, you displace billions of molecules. You change the flow of currents. You shift the alignment of nearby particles. You create a miniature wake, like a boat on a pond. That wake doesn't go away. It spreads, weakens, dissipates. But it never disappears. It becomes part of the story of the universe. And it's the same with you. You are not a temporary flash of experience. You are a pattern of lasting impact. Every movement, every word, every choice has a trajectory that continues outward, like expanding rings on water. This is the ultimate answer to whether the past still exists. You are the evidence. Every cell in your body is the endpoint of a chain of cause and effect, stretching back to the dawn of the universe. Your thoughts are shaped by language, which was shaped by culture, which was shaped by evolution, which was shaped by physics. You are not separate from the past. You are its continuation. And so, when we ask whether the past is still out there, we must also ask, have we ever truly left it? Or are we simply standing in its furthest ripple? Let's return one last time to the stars. The light we see in the sky tonight is not from the present. It's from centuries, millennia, even billions of years ago. The stars are not what they seem. Some may have already died. Some may no longer exist. But we see them now because their past is still traveling. So what about us? What if every moment we live also sends out ripples, photons, gravity waves, particle shifts, that will continue long after we're gone? What if those ripples are our footprints in time? What if we are stars to someone else, bright, distant, still shining after we've faded? This is not a metaphor. It is the truth, woven into the physics of the universe. You are not lost to time. You are made of time. And time, in its quiet way, remembers everything. Tonight, as we bring our journey to a close, we revisit a question that connects us all. Is the past still out there in the universe somewhere? This question, simple yet profound, touches on the nature of reality, memory, and our place in the cosmos. As we drift through these final thoughts, remember that this exploration is not just intellectual. It's a kind of gentle reflection, perfect for quiet moments before sleep. Throughout our journey, we've seen that the past is far from vanished. It is encoded in the light that travels across space, in the waves of gravity rippling through space-time, in the quantum information woven into the fabric of existence. It's preserved in atoms, etched in the structure of galaxies, and imprinted in the deepest patterns of the universe. More than that, the past is preserved within ourselves. Our bodies, our memories, our very consciousness are living archives of time, carrying echoes of countless moments that shaped us and the world around us. We've learned that time may not be a flowing river, but a vast landscape, a block universe where all moments exist simultaneously, or an emergent phenomenon arising from quantum entanglement and complex interactions. Whichever model you prefer, the evidence points to one clear conclusion. The past is not lost. It remains accessible, encoded in physical reality, in the geometry of space-time, and in the minds of beings who remember. Imagine for a moment the photons leaving your eyes right now, traveling outward, carrying a record of your presence to the farthest reaches of space and time. Imagine the ripples your actions send through the quantum fields, the gravitational waves subtly altered by your existence. These are not just metaphors, they are real, tangible imprints that will outlast you by eons. And as you prepare to rest, this knowledge can be a source of comfort and wonder. The past is not a closed door behind you. It is an open field stretching outwards, intertwined with the present and the future. Your memories, your actions, your very being resonate in the universe's endless story. So as you close your eyes, imagine yourself as part of this vast, timeless web, a thread woven through the fabric of reality, connected to moments long past and those yet to come. Sleep peacefully, knowing that time is not a thief, but a keeper. The past is still out there, waiting, not gone, but preserved. In light, in gravity, in quantum dance, and in the heart of all that you are. Good night, and may your dreams carry you softly through the echoes of time.